section of 1.4, we are going to give you a very general introductions of the type of functions that we are going to see. You have actually seen many types of function before in your secondary school. Okay, so the simplest function you can think of is a constant function that looks like this, right? So it's just a function that is given by the formula y equals to 3/2. I keep on wanting to write on the PowerPoint. Let me try again, ink. But the ink does not allow me to do it. Ink. Okay, maybe this one. Okay, maybe I can try to have an ink. I think I just better give up this. Okay. Okay. So let me come back to here again. I'm sorry. The simplest functions that we will see in the ZXA 111 is the constant functions. Now, constant function is a special case of what we call a linear function. So linear function is a straight line that when you represent it, it is just a straight line on XY plane. Now, a straight line or linear functions is described by two simple sort of like parameters, what to say. So here, this is the general formula that represents a linear function, right? So I would say the linear functions is the first type of function you would encounter in ZXA 110. It is defined by the form of mx plus b, where m and b are just constant. So if you change the values of m and you change the values of b, then the functions will change, right? So the m is called a slope and b is called the intersect. So different slopes and different intersect give you different functions. So this is a collection of example where you have a linear function where the slopes are different. Say for example, this is a function which has a slope of 1, a function with a slope of 2, and all the functions shown in these slides has an intersect b which is equals to 0. Okay, so when you set the values of the slope equals to 0 and set b equals to 0, that is if you set m to 0 and b to 0, then you get a constant. Okay, sorry, no, I'm sorry. When you set m to 0, then you get a constant function, and the values of the constants is the values of the b, right? So this is the b. When you set mx equals to 0, then the values of b will represent the values of the function that cuts through the y-axis. So this is an example of the of a constant. Okay, so someone is saying something to me. Enable drawing function. Okay, you need to open the PowerPoint in the form of slideshow first, then the option of pen will appear. Okay, let me try to do this. Okay, so then this is the function of the pen. It is not showing. Okay, let me try to do it again. pointer options. Okay, pen. So laser, pointer, and a pen. Okay, so I think yeah. Okay, thanks for telling me that, Nella. Okay, so now it's better. Now I can write something. Okay, so this is a function of y equals to mx plus b. So the special case is that when x equals to 0, then you get a constant function. So a values of y equals to b would looks like this, right? Where this is the values of y equals to b when you represent this graph, this function on a graph. So if in the case where b equals to 0, then y equals to mx, and then the example, sorry, okay, then the function of uh, fx would be just looks like this. Okay, so we are going to see and go through a list of different types of functions. So the first function is a linear functions. Then you also have, we are going to encounter a lot of what they call a power function. The power function is a type of function which is also very common. We are just repeating what the power function is. You have seen this, should have seen this in your secondary school. So the function that looks like this is here x is the independent variable and a is any constant, right? So a power function has a general form that looks like this: x power a, and a is a constant integer. For example, you could have, say, fx equals to a input variable, sorry, the independent variable x, and raised to a power of a, where a is a positive constant. It could be, say, x power 1, it could be say x power 2, it could be x power say 5, right? So this is what we call a power functions, a simple function, and the graph of the power function looks like this. Okay, so the power function would look like this. This is raised power 1. So if you look at this shape of the power function, you realize that this is actually a function which is y equals to mx. So this is equals to ax plus b, where b is set to 0 and a is set to 1, right? So you can think of this linear function as uh, well, a special case of power function. So it is a special case of a power function where the constants up here is equals to 1, and the slope and the intersect both equals to 1. Okay, so here a has a name. I think it's called an exponent or something like that, but we'll look at the power function in more detail later. So the important thing that you have to understand is that we are talking about here a linear functions. You should know how a linear function looks like and be able to know the general features of it. Say, for example, the slope is m and b is the intersect, and the general shape of a linear function is in the form that looks like this. Okay, wait. So the general form of an constant function is the form of a constant function is like this. Right? It is a straight line where the slope is m and the cut or intersect on the y-axis is b. Whereas for a power function, you should recognize the shape of the function, right? So if the a is raised to the power of 2, then the graph looks like this. If the power is raised to a odd value, or integer, then the graph looks like this. And if power 4, then it looks like this. And if it's power 5, it looks like this. Okay, so it's actually quite easy to recognize for a power function that looks like this. The power function where the a is odd is like this, right? Like this or like this. And if it's even, it looks like this. So these are the power function, and the range of the power function is from infinity to negative infinity. Well, from negative infinity to positive infinity, and the domain is also from negative infinity to infinity. So see, we are going to look at other functions as well. Power function, where the constants of the power is taking another value, which is negative. We are going to talk about polynomials, and we're going to talk about rational function. So we are giving you some general idea, some general types of functions, and we are going to deal with a lot of complicated functions in this course. So all the functions that we're going to see in this topic are the function that we will look into in more detail, including the domains, the range, and the shape of the function, and also other properties. For example, the symmetric properties and the divide dx, or the concavity of a function. But before we go into that details, you just have to know what type of function are there and the general features. Okay, so a power function, the constant there can also be raised to a negative value, a negative integer. So this is slightly more complicated. A power function that raised to power minus 1 looks like this. So this is y equals 1 over x functions. And if the power is raised to minus 2, then the shape of the function would look like this. So these are general knowledge that you have already seen in your secondary schools. So these are a special case of power functions where the range and domain are just as given, right? And when x equals to 0 in particular, the values of the function is not defined. And the domains of the function like this is ranging from minus infinity to positive infinity, but not included. So maybe I should write it here. So if you were to ask what is the domain of this function, the domain is from minus infinity to positive infinity. But well, or maybe it's not like this. I think it should be written as x should be included as from minus infinity to positive infinity. At the same time, this is a comma, okay? X is not equals to 0 and is included in a set. And so is the range. The range is also given by the same value, okay? The range is also given by a set of y, where y belongs to a set from minus infinity to positive infinity, but y can never take on values of 0. Okay, so for this case, the domain is for all values of x, but x equals to 0 is not included. And the range of y is just all the values from 0 up to infinity. So you have infinity on the upper side, and then you have 0, and both are not included. Okay, so this is how I write down the range and domain of a power function with the constant raised to power minus 2. So in general, given a power functions where the a is negative integer, you should know roughly the shape of the graph, right? So here I only show you an example of the powers equals to minus 1 and minus 2. Now you can also have a situation where the functions, the power function fx equals to x power a, where a is a ratio of two integers, say n and m, where n and m are just integer. It is possible to be like that. So this is slightly more complicated, okay? So let's say the power of a is 1/2, then the graph would be a square root function. And if it's 1/3, it will be a cube root function. and the range and domains are just as given, right? So all values of x is defined for fx. So sorry, for these functions, the values of the function is defined only for x that is positive. If x is negative, then the function cannot be defined, right? So the square root of a negative value is not defined. So the domain is only a positive value. Whereas if you raise the x to the power 1 over third, then the values of the function is defined for all values of x over 2. Okay, so if you look at this situation, x raised to a 2/3, this could be understood as x raised to the power 1/3 and then you square it, right? So remember your rules for an exponential function. If it's like this, you multiply this by b, then this is the same as xa raised to the power of b, or vice versa. Okay, so 2/3 could be understood as 1/3 times 2. So this is a function which is cube root function. So a cube root function squared. So the domain of this is what? So for this particular case, the domains of the function is defined for x negative or x not negative. The answer is that the domain is defined for x, which is defined for all x from positive to from negative infinity to positive infinity. How about this one? The domains of this function x raised to the power of 2/3 is also the same, I think, right? So these are tricky questions, but if you think about it slightly more deeply, you'll be able to understand the range and domains of these functions is for x from minus infinity to positive infinity. Okay, maybe I stop for a while to see if you understand this slide. Now, sometimes it's very confusing, right? To me, sometimes when the powers is raised to fractions, the functions for the denominator in the a, if it's even, then the domains cannot include the negative sign. So this is power 2 in the denominator. So this is a factor of 2, which is an even number in the denominator of the power a. Then the function is not defined for x in the negative side. And if the denominator in the values of a is an odd number, then the function is defined for all values of x. So it is quite straightforward to look at the graph. So this is a graph for x power 1 over 2. So this is a function of x power 1 over 2. So this is an even value in the x. So the function is not defined for x negative, it's only defined for x which is positive. Okay, so here it is an power of 2 in the denominator, so it's also not defined for function which is negative. But if this is x raised to the power of a ratio of a, which is equals to 1 over 3. So 3 in the denominator of a, right? 3 in the denominator of a means that this power function is defined for all values of x, including the negative side. So this is the same. The power of a is whatever number divided by an even number, odd number. Then the function is defined for all values of a. Okay, so this is the features of a power function. Then we are also going to see polynomials. Polynomial function is also a very important types of function and it's very general. So you see polynomial functions everywhere in your in this class as well. So a polynomial function is made up of n terms. So if you can recall your secondary school, you should also have learned a polynomial function. A polynomial function has one independent variable x, and it has n terms. So n could be an integer. So for example, if n, just example, if n is equals to 2, then the polynomial of order 2 is written as a 2x power 2 plus a 1x power 1 plus a 0. So an polynomial with degree n equals to 2 has 3 terms, right? And the highest power in the polynomial is the order, right? So if it's order 5, then the highest power, if it's n is equals to 5, then the highest term in the polynomial would be then a5x power 5. And the other terms would be with power which is less than. So you add it to a1x power 1 plus a 0. And in this case, all the a's, a1, a2, a3, a0, up to an is what we call the coefficient. Okay, so a polynomial of degree n has a highest order term with x power n, and it has coefficients starting from a0. So a0 is just a constant which is not multiplied with any variable x. So a polynomial has coefficient an minus 1, an minus 2 up to a0, and the highest order in the polynomial is x raised to the power of n, where n is just an integer. So polynomial is also a very important type of function. So a polynomial is completely described by the degree and also the set of coefficients. So when you talk about a polynomial, tell me what is the values of the degree, and then you also have to specify the set of all the values of n. So once the set of n is specified, for example, you say n is equals to say 2, then a2 is equals to 1, a1 is equals to say 0.5, and then say a0 is equals to 0, then this would refers to a polynomial of order 2 and is written as x power 2 plus 0.5 x power 1 plus 0.5. So importantly, to specify a polynomial functions, you have to specify the values of the degree and also the set of all the coefficients in the polynomial. So once these numbers a2, a1, a0 is given, then the polynomial is completely specified. And these are the example of the polynomial. So this is a polynomial of order 3 with a coefficients 1/3. And this is a term which is power 2, coefficient is minus 1, 2. And the constant here is a0, which is 1/3. This is a polynomial of order 4 of degree, not order of degree 4, with a coefficient of 8, and the highest term here is power 4. Okay, so this is an polynomial which is of power how many, right? So you can count. So if you open up this factor, it's power 4, then this will open up the highest power in x for this term is this term is power 3, this is power 4, this is power 1. So this is a polynomial of order 8, okay? But it's just expressed as a product of 3 factor raised to different orders. Okay, so but basically this is an polynomial. Now this polynomial, although it doesn't look exactly like this form, but it is understood to be just a polynomial. It's just expressed in a factorial form. Okay, then you have also a rational function. A rational function is made up of quotients of two polynomials. with the condition that the domains of this polynomial is such that the values of the x for qx cannot make qx equals to 0. So let me say it again. A rational polynomial, a rational functions is a ratio of two polynomials, and the domains of this type of rational functions is where the values of x cannot be 0. So the values of qx cannot be 0. Okay, so these are the example, right? So if you look at this one, for example, if you ask a very simple question, let me say it. Okay, so if you ask a very simple question, what is the domain of this function? So the domains of this function is the set of all x, where x is from minus infinity to infinity, but the x cannot be equals to minus 4 over 7. Okay, because if it's x is equals to minus 4 over 7, then the values of the function is going to be infinity. So this is the domains of a ratio of two polynomials with the condition that the domains inside the domains of these rational polynomials cannot be defined to be 0 for the denominator polynomial. So a rational function is made out of the ratio of two polynomials. That is it. Now we are going to look into this more detail later on. So in particular, we will learn how to sketch the graph of a rational polynomial. These are just examples. You're not expected to be able to plot this graph at this moment, but later on we will teach you how to step by steps systematically construct a rational polynomials. Okay. So here this is called the asymptote, horizontal asymptote, vertical asymptote. I will look at this horizontal asymptote and vertical asymptote, and I think this is called oblique asymptote. Right? This is a line which is called oblique asymptote, which we will be talking about later, but not at this point of time. Okay, I have a few more minutes to go. Okay, so then you could also have what we call an algebraic function. Algebraic function is a generalizations of polynomial function. Okay, so let me go back and polynomial. See, polynomial is made up of power functions, right? So power functions is like this. Power function is a generalizations of a linear function. Okay, so this is a linear function. So linear function is a special case of power functions, and power function is a special case of polynomial. So for example, if you set all the coefficients of the higher terms all to 0 and you set a(n) equals to 1, then what you end up is a polynomial with x power n, and that's nothing but just a power functions, right? So when you take two polynomials to construct a rational function, then you have a rational function. The rational function is a generalization of polynomial functions, in the sense that if you set qx equals to 1, like if you set this equals to 1, then what you get is a polynomial function of px, right? So so a rational function can be considered as a generalization of a polynomial function, whereas algebraic function is a generalization of polynomial function. So you take any polynomial functions, then you perform some algebraic operation on it. For example, if you take say for example this one, so if you take a function of x power 3 or 1 over 3, and then you multiply it, which is a multiple operation, with another polynomial, which is x power 4. X power 4 is a polynomial of order 1. So you have two polynomial which is multiplied together. Then what you form is an algebraic function. Now this is also can be considered as an algebraic function. So for example, you have a polynomial which is 4 over 3. Now 4 over 3 is a constant, right? So it's a constant can also be considered as a polynomial, which has only a degree 0. So a constant function is a polynomial of degree n equals to 0. You multiply this with an polynomial which is of degree 2, and then once you got this polynomial, then you operate on it another operation which is to raise this polynomial to an order of 2 over 3, right? So then you multiply these functions together, then you get these functions. So a polynomial of algebraic function is a polynomials is formed from polynomials by carrying out algebraic operation on it. Okay, then we also have trigonometric functions and exponential functions and logarithmic functions. These are all the functions which you are going to see in more detail in times to come. So we are not going to talk too much about these log functions, just to let you know that we're going to see this again in later chapter.